Okay, I think it's probably time we should get started. Today's talk is on antennas, more than just metal coat hangers with aluminum foil. Our speaker is Randy Bancroft. He's a longtime member of the Hub and an electrical engineer. Let's just do that. You can start.
Let's see if I can figure out there. That works. Okay. All right. All right. Oh my goodness. Okay. Well, let's get started. So, back when I first took antennas years ago at Iowa State, Dr. Stevenson, who was probably my favorite professor there because he was a very patient man, had 3 antenna rules that he told us the first day. The first one is, everything is an antenna. Second one is, for every transmitting antenna, there should be at least one receiving antenna. And the third one, you don't have to really understand, is if you're transmitting in the near field of another antenna, it's best just to speak with the person or hand them a note. So, actually, all the space around you is essentially like your coax that brings electromagnetic waves. Circuits people say voltage and current, but there's a wave in there shooting along. And that wave comes up, we give it to the transmission line of free space, which we go from 50 ohms there to 377 ohms in space, and then we take it back down to 50 ohms again, and then you can watch television. And the reason, if you're curious about why it says 50 ohms on a coax, is if you have an infinite length of coax and you put any sort of device on the end of it, it will look like a 50 ohm load because it goes on forever and the power never comes back. So literally there is a reason it says 50 ohms, even though where's the 50 ohms? Now, one thing I'm hoping you can get over a little bit tonight is the prejudice that I have to put up with by being an antenna engineer. And that is that people don't like them. They want to hide them. They don't want to be seen in public. And here's that's just, 50 to 377 to 50. You end up with situations like this, where, it says top there, it says, don't mind us, we're just putting the lid back on the cactus. So they're basically hiding antennas inside of fake cactuses and everything else so that, you don't have to look at such horrifying things. Hopefully, maybe I can help you see some beauty in antennas tonight. Okay. So, why should we use an antenna? Why even bother? Well, this is out of Milligan's book. You don't have to read any of this stuff. But this is a pretty interesting calculation. And what it shows is if you take a couple of antennas and you set up a link and you take the same piece of like waveguide, when you go 2 kilometers, the waveguide's way better. It's like 40. And the antenna loss is like 88. But by the time you get to 10 kilometers, you end up with a waveguide loss is 197 dB, and the antenna path loss is only 102. At some point, as the distance is increased, antennas eventually have lower losses than any cable. So not only is it easier to string the cable because you don't have, it's already in space, it works better. And for those of you that 95 dB difference here between 197 and 102, that's 1.58 billion times worse loss than an antenna link. So that's one of the reasons. Now, metal has a lot of electrons in it. So you have a piece of metal, and it's like a balloon filled with electrons as the gas. And the electrons can go anywhere they want to. And so if you take these electrons and you grab onto them and you shove them up and down, they're being accelerated. And whenever they accelerate, they radiate an electromagnetic wave. And this is done 3 different ways, simplified a little bit, just a tiny bit. So when you're in your car you hit the accelerator and you're going in a straight line, and you feel it push you back, that's an acceleration. So if you can take these electrons and you shove them there and you shove them there faster and back and forth, they're accelerating. And so they will, and this is the sort of thing you see on a dipole antenna. Now, when you turn a corner, you feel an acceleration. And so when that happens, if you have electrons and you make your wire kind of turn, you can end up with acceleration. That's all antennas do. If you accelerate electrons, they radiate. That's just what they do. Or you can guide a wave inside of a metal pipe or inside of a coax, and then transition it to free space, not unlike a dish antenna. So that's about, mostly, we'll talk about one other one. But by the way, every object above absolute zero, and I think everything in here is above absolute zero, has jiggling electrons that radiate electromagnetic waves. Dr. Stevenson was right. Everything is an antenna. They're all radiating electromagnetic waves. The tables, the chairs, us, you, everything. And I guess astronomers care about this. You can determine temperature from the radiation. A lot of times they'll take antennas and they'll point them at something, and you can tell what the temperature of something is just by pointing an antenna and measuring the amount of electromagnetic noise coming off of it. So this, probably can't see it super easy, but that's a dipole. There's just wires that are just basically a big wire. And this is the old Russian woodpecker antenna, and if you want to get on the internet, you can find out all kinds of really great conspiracy theories about this, including the fact it caused Chernobyl to happen. But this was a low frequency antenna. And here is a helix antenna. You see it spins around. So you've got, in this case, you've got the electrons go back and forth like this and radiate. In this case, going around, and you get some acceleration again. And now I'm going to talk about one of my favorite antennas, which is the Voyager antenna. And I had the good fortune of being a office mate of the guy who developed this, M.S.E.E. And I love this thing. It's pretty amazing. This is 2 gigahertz, and the way this works is right down here is a high frequency waveguide, and so it radiates out of that waveguide. And on this side, there's a very, very thin sheet of plastic with a bunch of little copper X's on it. And those copper X's are all tuned so that they will reflect right at that frequency. So it comes up out of here, and then bounces there, and then comes back to the Earth. But M.S.E.E. was able to get a 2-for-1 on this antenna. It was really cool. So the S-band one here, these X's, they don't resonate at the S-band down at 2. So this one is another waveguide, and it shoots directly down at a second frequency and bounces up. So you get 2 different frequencies. And that's called a dichroic subreflector for anybody who wants to know. So at any rate, and it has about a 3.66 meter diameter, 25 watts into it, and it's 20.4 terameters from Earth right now. And you all know that's at least 25 times 10 to the 9th kilometers, right? So it's a long way. And the Earth received power is 90 zeptowatts, or minus 160.48 dB with respect to a milliwatt. And that is really tiny. And those, they have 70-meter dishes and really low noise amplifiers, which we'll talk about a little bit, so that they can even hear this. I mean, this is astonishing and the farthest away human-made object. So, don't get too scared here. It's not a big deal. This is a dipole antenna. So you feed it so that the currents go up, and then they go down, they go up, and they go down. And it creates an electric field like this that moves out. Well, if you have an electron and it's just sitting out here doing nothing, as these waves come by, they go, the only thing an electric field does is shove around electrons, at least for Maxwell, and up and down, up and down. And as that wave comes by, because metal is a gas of electrons, it'll shove whatever electrons are in there up and down. Yeah?
Sorry, could I ask you to go back a little bit to more basic stuff?
Oh.
And because I think a lot of us here might not be familiar with the principles of antennas at all. And so the idea that you're feeding some frequency to a length of what
Just wire.
How's it work? Yes, but just wire, but
There's electrons, and whenever you shove an electron up and down, it radiates a wave.
what makes it go up and down?
You put a voltage, you get a little voltage thing, and you put the voltage right in between here, and it shoves electrons up and down in response to that voltage.
But how does that fit with the length of the antenna, the size of the antenna?
Well, the size of the antenna, I'll mention that in a little while here, but the length of the antenna is proportional to the frequency. So if you have a higher frequency, it gets shorter. And if you have a lower frequency, it gets longer. And that's kind of the way, that's just a truism about antennas. But here is what it looks like from Wikipedia. Here's what it looks like when it's going back and forth. So you basically have this current going up and down and up and down. And these bubble-like things come off of electric fields. And if you have an electron sitting here, it just goes up, down, in response to whatever the up-down is in here. So if you move this one, the voltage goes up and down and you shove them up and down. These waves that come out are proportional exactly to however you shoved them up and down in the middle there with a source, with a transmitter.
Does that mean that the signal will only be picked up by an antenna that has the same characteristics?
Yep, absolutely, that has the same frequency. So the physical length of the antennas is proportional to the frequency at which they operate. Now the distance between these bubble centers here, that's the wavelength. And because the speed of light is constant, how fast you do this means how far the bubbles are apart. And so let's see, bubble centers. I always like to look at it like, when you were a kid and you had bubbles, Okay, well, we'll get something. This is just a basic little thing, and we'll talk about the antenna on the Titanic. How about that? So here is the antenna on the Titanic. And interestingly enough, the radiation is from this section right here. It turns out that there's ocean out here and there's metal down here. And one of the principles of antennas is if you have a conductor down here, essentially you can take the ocean away and pretend you're just floating in space, and there's an exact image of this. And it turns out that all of this will cancel, and this is the only part that radiates at all. So this actually is omnidirectional, and a number of, in Wikipedia and other places, a lot of people think that this entire thing radiates. It really doesn't. But what was interesting was when Marconi was working on this, he was just guessing. He literally was guessing. He didn't know how to make an antenna. He knew that he had something sort of like a capacitor. He knew that he had something kind of like an inductor, a big coil, so you need a big capacitor and a big coil, and you got to shock them somehow. So fortunately, the original Time Tunnel TV series in 1966, the very first episode was about going on the Titanic and trying to save it. And of all things, they had a really kind of neat, they showed pretty much what it probably looked like. So there's the spark. They would do a spark, they'd zap it with a spark, and there's a coil and then the antenna. And they will go back here, and down here in a minute or so, you'll see there's the spark. And then there's a coil you'll see here at the very end. And then the up here is where the antenna appears to be connected. So, come on guys, there it is. See the coil? There's the coil, there's the antenna, and there's a spark. So all they're doing at that point is they're just hitting this thing with a spark and hoping waves come out of it. and producing something resembling. And Marconi was all trial and errors. I mean, he really literally didn't have any idea what the hell he was doing. The Titanic was not the first vessel to use wireless to call for a rescue, but, and if you're really interested, and thank you, Becky, this book is really great called Thunderstruck that talks a lot about how Marconi ignored people like Oliver Lodge and other people that were very knowledgeable and went ahead and did this anyway and became lucky, very lucky. Now,
Morse code at that time?
yeah, I think so. It was, yeah, SSS, right? When they,
Yes.
yeah,
That would be international Morse code.
yeah, that's, yep, and,
There was another Morse code that was used by American railroads,
interesting.
but they would have been using international Morse code.
And the original of this, the original, when they did the sparks, they were so loud they sounded like shotguns going off. So you didn't want to have the your room near where the transmitter was there, because you wouldn't do a lot of sleeping. And he just put more power in it. Now, don't get too freaked out here. It turns out that plastic non-conductive materials can confine electromagnetic waves. This would be like fiber optic, where you're sending light, which is an electromagnetic wave, down via fiber optic. I don't know if any of you ever swam with goggles at a swimming pool, a public swimming pool, and noticed that you can look straight up when you're underwater and see, but then it looks like a mirror as you get out further. Well, that's because at a certain angle, the light reflects perfectly, so it gets trapped. So there will be a reason for this. Here's a coax to waveguide transition. So we got our 50 ohms, and we go into this pipe. Then we go into this dielectric rod right here, and it captures the wave, and then it moves it into free space. So right here, this is usually plastic, ceramic, or some other non-conductor that will trap the wave. And here is why I bother bringing this up. There was, years ago, there was a method called the finite difference time domain that was that was in electromagnetics. You needed to have computers big enough to compute Maxwell's equations. Well, one of the early ones that was done was this by Melinda Pickett May up at CU, actually. And this is the electric fields inside the dielectric rod antennas that are in your eyes. So this is the rods. These are the black and white. There's about 92 million of them. There are papers that talk about the color ones that are cones, but they're boring and don't have cool pictures I can show you like this. And so the first thing she did was they know all the dielectric and all the properties needed to do this. And so this is one of the first things. It's kind of amazing to think that we evolved this. So that the back end here goes to your optic nerve, and you can see things. So you have a lot of antennas in here. And this is the electric field strength magnitudes. Now, I do have favorite antennas. And this is one that I love. I just can't help. I take a shot of one whenever I'm traveling or if I see one. And this is called a horn reflector array. Shot this in Minnesota. This is on Bell telephone links. And these were used to basically send telephone calls back and forth to one another. And so here's one that they were invented by Alfred Beck and Harold T. Freese, Freese is very famous in antenna engineering. Here's one where it has round instead of this shape. And then I got one here, and I tried to figure out why this looked different. It has these funny edges here. And it turns out that those funny edges are there because an antenna will always see a little bit of radiation from behind it. So it's supposed to see everything coming this way. But there'll be a little bit it can see from behind. And that looks like noise. So the lower that you can get that, the less noise the antenna has in it. It'll see noise temperature, which we'll talk about. So here, Dr. Stevenson showed me, this is really neat because what it is you have what's known as a horn antenna. So this thing creates waves that are very planar, and then they come up just like a parabolic dish and come out this way. This was invented by Fries, and Shelkanoff talked about it. At any rate, waves come up here, they bounce, and this thing is actually better than a dish antenna. Has 70% aperture efficiency, and it's very low noise. It doesn't see any of the other surrounding noise around it, which makes it just, I don't know, I always thought this was really a cool antenna. Other people did too. This is these two fellows measured in excess of antenna temperature. So they said measurements of the zenith noise at the Crawford Hill, let's see, yielded a value of about 3.5 degree Kelvin higher than expected. So they were quite surprised, and they said, well, we looked up and we saw more than we should see. They said we don't see any seasonal variations. And they said they couldn't figure out any way that this was a thing, because they said, well, a possible explanation is given by these other guys in a companion letter. So they said, yeah, we don't know what it is, but these other guys have an idea. Well, we're not too crazy about it. Well, yeah.
What's the temperature they were referring to?
They're referring to I'll have it here in just a second, but what happens is, I said everything's an antenna, right? So if you have metal here, it's going to have a temperature, and electrons jiggle back and forth. So it's going to end up looking like received power coming back in. And so you have to count that. So there's a temperature that's associated with that. And people use noise temperature instead of, there's a thing called noise figure. Noise temperatures you just add because they're temperatures. They're very easy, and that's why people like to use them. So there's the temperature from this. Then there's the temperature, in fact, I'll just do this. 2.3 degrees Kelvin is, everything's an antenna, right? Well, they knew that above the atmosphere up here, you can calculate it all. It's going to be 2.3 Kelvin. And so what's beyond the upper atmosphere? Nothing. Well, everything's an antenna, but if there's nothing, then how much noise should we get? Nothing, right? So we got nothing up there, so we know what the atmospheres are doing. We know that there's 0.9 K from the losses in the copper, the ohmic losses, and the back lobes, which is the fact that antennas always see a little bit. Now this Earth down here is 200 and some K. So a little bit of it comes in, and they go, well, we've got 2.3 there. We got 0.9 there. But we're measuring 6.7. I mean, look at that too. I mean, that's significantly large when you're talking 2.3 and 0.9. That's not some little error. Well, so what is the 3.5 K antenna temperature? Well, there's nothing out there beyond the atmosphere. So it turns out that the two guys who did this were Penzias and Robert Wilson, and they didn't like the Big Bang Theory much. They said, well, you know, they didn't like Gamow, and forgive me for the pronunciation of Lemaitre, this was the first evidence that existed, but the authors did not claim it as evidence for the Big Bang because they weren't crazy about the Big Bang. Down here they go, oh yeah, these other guys in this issue, they give this reason, but we know there's nothing out there. Everything's an antenna, there's nothing out there. Nah, it's somewhere else. There's some other loss in here that we don't know what in the world it is. Well, no, that's not what happened, and they won the 1978 Nobel Prize for physics for their discovery. And don't forget that Nobel Prizes are for discoveries, not making the best guess what the heck it was, necessarily. So it turned out that yes, indeed, that temperature was because there's nothing out there. What the heck could it be? It's the Big Bang. And now we spend quite a bit of time trying to find out what the temperature is, and this is one of the latest maps of it, and these different colors here, I can't even express to you how small these are, these differences. I remember when I looked it up, it's absolutely shocking how little change in temperature there is. You know, I don't remember right off, but it was unbelievable.
What is that an image of?
This thing is, they now take antennas. This one, they just pointed up and went, yeah, we see this extra crap. We pointed over here, it's extra crap. What they did, this one is a map of the entire universe. And they're looking, they send up these satellites and they go, okay, we want to know this, we want to measure this. And what they did was they plotted it as temperature. And this is the differences of temperature of the Big Bang.
So this is background radiation?
It's background, yes, this is it's the background radiation from the Big Bang.
And
Yes.
the fluctuations are millionths of a Kelvin.
I thought they were incredibly tiny. Thank you, Clyde. They're incredibly tiny. I mean, it is really, yeah, millionths of kelvins. Thank you, Clyde.
If I could add one other thing.
Sure.
If that were absolutely the same temperature everywhere, we wouldn't be here.
Wow.
Those fluctuations are what caused galaxies to form.
Nice. Nice.
No, this is
No,
the temperature. You
it's
point
just the
your- point your
temperature.
antenna, and at each point you can measure, and it's accurate enough to measure the difference between the average and the particular spot, and those are in the order of microkelvins.
Yeah.
Why does that cause?
Because the density fluctuation, if the universe were absolutely the same density,
Oh, no, because
nothing would,
the density or temperature?
they're the same. The temperature is going to map the density.
And so we spend an incredible amount of money on this. The modern value is 2.73K rather than the 3.5, which was close. And apparently it's used to determine the Hubble constant. So whether the universe is expanding, contracting, whatever your fudge factor is here, that's really become important. So it's gone from one of my favorite antennas that's super low noise to something really, really important. Well, now there's a type of antenna called a Yagi-Uda antenna. Now, this is probably next to a dipole. Any technician that's ever worked in antennas knows what a Yagi is. Everybody will say it's a Yagi. So you can, say Yagi, and you're part of the antenna crowd. And what it is here's this dipole right in here, and you're driving it, and those waves are coming off. And so what happens is, if you go, and this is a quarter wavelength, which is important, the wave that comes off this side of the antenna will hit this, and just like those crosses on Michelle's dish antenna, this is tuned so that it will reflect. So the wave that comes here reflects and comes back this direction. And so this is known as a reflector. And when this wave plus the wave coming off of this side meet right here, it creates a current here that adds this way. And that's called a director, because it directs it. So the other thing that you need to know about a Yagi-Uda antenna is that usually they're fed with a folded dipole. And you'll see coming up why I bother explaining this. But you see this round thing right here? Usually that is in here. And there's various reasons for that. Usually it has to do with how you feed them. Now the antenna pattern here shows that almost all of the energy comes up here, and here's that back lobe like I talked about on the horn antenna. So this back lobe is really small, so if you're on this side of the antenna, you're transmitting, you'll see a little bit come out, but the majority of it will come shooting out this way. Now, this antenna was created by Mr. Uda, Mr. Yagi, and I've never been able to get a really good story. Wikipedia has their story on this. And what happened is in 1926, apparently Professor Uda in Japan came up with this. However, Mr. Yagi went ahead and patented it. And I hear different versions of this. It's rather contentious. Some say that Yagi was also the first guy to publish it in English so that the English-speaking world could read it. And here just is a Yagi-Uda TV antenna. So you've got here's your folded dipole, here's your reflector, and then you can have more than one director. And it goes off that way. So, I was down with Don at the, yeah, there you are, folded dipole. I just have them pop up and show you the directors, the reflector, so on. We were down at the Nuclear Museum down in Albuquerque, and they had Fat Man and Little Boy, and they had these proximity antennas on them. And of course, I had to go up and take a look to see what on earth these were. Remember when I talked about the Titanic? And if you have a conductive plate, you can actually slice an antenna in half. So if you have a dipole, you can slice it right through the middle, put it over metal, same thing. The directors, same thing. So this thing is called, it was the Archie radar antenna, the altimeter. So what this antenna did was, as this thing is falling, it's transmitting electromagnetic waves. They're bouncing off the ground and coming back up. And this will tell you how high it is. And people had calculated, where do you want the bomb to blow up? And so this radar, which by the way, I'll give the British credit here in America, they came up with the system that this is based on. So this antenna right here, actually there's 4 of them so you can see all directions, but as it's, of course it's going to go this way. Well, here's a close-up of it. And when I looked at it, I was a little surprised when I was down there because that's a reflector monopole, because this thing's all made of metal. That's a folded monopole, which is half of a folded dipole. And that is a director. So it's all going to go, this is the direction of the pattern. Radiation pattern is going to go this way. As it's falling, it's going to see it. And of course, as you can imagine, you may have figured this out already, they called it a Yagi-U because it's a Yagi antenna that they put on the atomic bomb to drop it on Japan that was used, a design that's one of the most known in the world by 2 Japanese professors. Oh, and it took me a long time to find out, but it was about 320 megahertz. The British ratted it out finally. So, we'll talk about Schumann resonances now. Now, if,
that had to be that high because of the size of the antenna?
oh yes, yeah. In fact, what's interesting about this is I found the drawings. I didn't put the drawings up here for you because they show the distance from here to here to here, but they don't show the length. That's the only thing that would give away what frequency the antenna operates at. So I was going to go back and calculate it. I went back, looked at the drawing. The drawing has a break in it, and there's no dimensions on any of these in the documents. So they didn't want you to know. They didn't want you to jam it as it was coming down. No, good question, because I did find the drawings, and yes, and the length is exactly where the 320 comes from. So those are probably, if I remember right, about like that big. Makes sense. Okay. So here it's kind of interesting is we're going to end up talking about Schumann resonances, but before we talk about that, what was discovered was, remember I was talking about Marconi. And Marconi, he was a pretty lucky dude, because Oliver Lodge, who was really pretty sharp and also into spiritualism, but he still was pretty damn sharp, he knew, and others did, that, well, look at my laser pointer. It goes in a straight line. Electromagnetic waves go in a straight line. So I'm standing over in Britain, and I'm going to hit Nova Scotia. This is round. So they were all saying to him, look, dude, you're going to shoot that off and it's going to go flying up into space. Because yet again, there's nothing up there, right? Well, they didn't realize that there is this thing called the ionosphere out here that looks like a bunch of electrons. And they're jiggling around just like in metal. And the Earth itself is also conductive. So Marconi, not knowing, didn't know that this was the case, but having a lot of money and a lot of guys that had money, he started trying to send it. And he got lucky because it would hit this and come back down. And he did notice early on that depending on the time of day, he could get better reception on the ships as he was going away, because this actually moves and is more, I believe, stronger. So at any rate, you can see why Oliver Lodge and these other guys said, you're just barking up the wrong tree. They're just going to go flying out into space and it's not going to work. But Marconi got it to work. He kept trying, and as I say, he got very, very lucky. And it goes between these two conductors. And this is like a waveguide. Yes?
When he was trying to get it to work, had he intuited that there would be some reflection?
No.
Or he was just playing?
He does not strike me as technically savvy in almost any way. He was one of those guys that he was a little P.T. Barnum-ish. He just was sure this would work for some odd reason. And, well, yeah?
Just throwing stuff against the wall.
Yes, he was throwing stuff against the wall and hoping something would happen. He was basically your dot-com entrepreneur and said, give us a bunch of money and we'll make this happen. And he got lucky. Because if this wasn't there, Lodge would have been right. And there would have been no transatlantic communication. So, yeah, sure.
Isn't there some refraction in the atmosphere?
Well, what little refraction there is tends to bend the wave this way anyway. And so if you notice, you're at the ground and it's hot, right? And it's hot and then it gets cooler and cooler. If you look at the way light travels through density, it'll do this. So there will be some of that, but this is a much bigger thing. And you see the one you're talking about, you see when it's the other way around on a hot day, and you'll see that what happens is it bends this way. I was talking about looming. That's my mistake. I'm screwing it up. But what you'll see is you see the sky and you'll think it's water on the road. But that one does exist, and it does happen for electromagnetic waves, and they get bent. But this is the primary, because this is more like a hunk of metal, more than that effect.
But that covers large distance, not small. So you don't get radio transmission for 100 miles, you get radio transmission for 1,000 miles.
Right, it's right. It works a lot further. It's because, you just...
How do you get, because sometimes you get radio transmission for 100 miles. How does that work?
Oh, God. I belong to the Antennas and Propagation Society. The discussion of how these things propagate is an entire field in itself. We can talk about lots of very strange things that happen with electromagnetic waves. Let's see, a guy by the name Wilfred Otto Schumann lived until 1974. He realized that this geometry existed. And it turns out, remember that spark gap generator? They zapped that on the Titanic? Well, about every 50 times a second, 100 times, depending on who you talk to, there's lightning bolts all around the world. And they drive these resonances that are standing wave resonances because this is a waveguide. And I found this a little bit too interesting for my own good. The first one, the fundamental mode, the first ring of this bell-like thing, you might say, is at about 7.83 hertz. That is really, really, really slow. That is a really long wavelength. The second one is 14 and 20. And showing that sometimes I get a little bit obsessed with things. While I was living in Indianapolis, I decided I wanted to detect these. And this has about 57,000 turns on a metal rod, and it's 27 gauge wires. And thankfully I had a whole bunch of really good circuit people that helped me create this amplifier, and here's what this looks like inside PVC. And this is a 132 dB amplifier, which when I did it was absolutely crazy to do, DC coupled. But apparently I was bored. And by the way, 132 dB is 15.8 trillion. Yes?
What does dB mean?
Oh boy. It stands for decibel, and what it is a way to, it's a way for engineers developed years ago to compact really large numbers into small ones. So for every 10 dB is a factor of 10. So 10 dB is 10, 3 dB is 2. So 13 dB is 20, 20 dB is 100, 30 dB is 1,000. So it's almost like the number of zeros behind there is kind of like it works out. So 40 dB, you know, and so on. You just keep adding 10. If you, I actually have written quite a bit about this because I don't like kind of the way things are done. But it's along the Bell Telephone Company pushed the decibel so that it would be a thing. And I have a write-up in one of my books about all of the back and forth on decibels. But the thing is because they use a logarithm, they take the logarithm, it compresses it. And you know, that's one thing Dr. Stevenson also said is get comfortable with decibels. If you can say it, you know, and know what a decibel is, any number of engineers that are party, you've already got them beat. They think you are one. So one night at 1:43 a.m. In 1998, I was running this contraption, and right there I saw, right at 7.8 hertz, what looked like the first Schumann resonance, which surprised me. I took it into a couple of signal processing engineers at the place I worked in Indianapolis, and both of them said, yeah, that looks different than everything else. I think you did this. So I sent it to a professor who actually measures this for a living, and he said, yeah, I think you did it. And then he couldn't believe I did it in the middle of Indianapolis. So that's, I'm telling sea stories. Now, this antenna is known as a Vivaldi antenna, and this one I designed for ground penetrating radar. And remember I told you that, you know, here's an if you go around a corner, you're kind of accelerating, so you're making things happen. This is what I like to call a self-scaling antenna. So it will radiate, the high frequencies radiate in these little areas because short is higher frequency, and the limit is here. So this thing went from, well, it goes from at least 400 megahertz to like 6 gigahertz. And I developed this for ground penetrating radar. What they can do is you shoot electromagnetic waves into the ground, and you can, yes, Chauncey?
I just can't quite tell what I'm looking at here. Are there wires on there?
What there are here is, this is copper, see all the copper colored stuff here? And then this is a wire, it's sandwiched. So this is a wire that's in between two plates that have this shape. So there's a top plate that looks like this and a bottom plate, and then this one runs in between the two, and it feeds the antenna right here. Forget about this. This is there only to make the wave go this way, is the only reason it's there. And so the wave comes down along here, and then as this taper occurs, it radiates off. And the idea behind this was they need lots of, it turns out the number of frequencies you have gives you resolution into the ground. So you're looking for pipes, water pipes, I don't know, dead bodies, Jimmy Hoffa, you know, something. But this is the one that I did in a computer, and here's the one that was built that they used as proof of concept. The good news is it worked. So I'm just kind of showing you different types of antennas. I don't know if that's all that interesting. But here's what I've always been interested in, because I can't hardly believe these things. These are this is what I do, microstrip patch antennas. This is essentially metal, plastic, metal, and that's it. And when I first saw this, when Dr. Stevenson showed me this, I went, oh, you know, you just spent basically a semester explaining to us why you shouldn't do this. So it was quite a surprise to me. This one, this one has what's known as a TMO2 mode. So if you've ever seen sand placed on metal before, and they take a bowstring and it makes these beautiful patterns, that's, in electromagnetics, this makes a pattern of currents, and that makes a radiation pattern. This one actually has no radiation right off of it, and it goes in kind of a butterfly sort of pattern. This one, different mode, goes shooting right off of it. Now, believe it or not, when I first started working with these, I mean, look at that. It's a hunk of copper, plastic, hunk of copper. That required some of the most complex variable analysis you can imagine. And I just couldn't imagine. This problem seems so simple, yet it was confounding for people.
So is that dependent on the spacing or the mass?
Oh, the spacing between the plates? We'll talk about that. It's the only thing I've ever done in antenna engineering I'm almost proud of. But yeah, it depends. When you do the spacing, the frequency doesn't change much, but the amount of power that comes out does. Now you can take, this is a microstrip array that I fixed for some people, and the thing to keep in mind is these are just like you're under a waterfall, and you've got a small funnel, and one of these is the funnel. Well, if you want more water, you get more funnels. You add them all together, and you bring them together here at one place, and you get more water. So if you have an electromagnetic wave, it has a bunch of power coming in, this thing grabs more of it out of the wave, because you can just take and cut the wave and pull the power out of it.
So it's very directional.
Yes, right there. Yes, it is very directional. And this is the actual, what it looks like, the transmit. Well, it works both ways. But yeah, this is what the pattern looks like off of this. Lots of power up here because it all adds together. And it works both directions. There's a thing called the reciprocity theorem you don't need to know about. But transmit antennas and receive antennas do the same thing. But yes, this is basically showing off of this thing, you get a lot of power, or you receive a lot of power. And it's at 24 gigahertz, which is pretty high. Oh, and I had to talk about the one and only thing I've been sort of working on lately. This is kind of fun. There's a company, Vertus Solis, that I've been doing some consulting for, and they want to do space-to-ground microwave with rectennas down here. So they're going to have this thing up in space, supposedly shoot down microwaves and turn them into DC so that we can, you know, we can run our toys. And this is the antenna that I did. See the antenna? Yeah, microwave power sent from space, direct current. Oh, it was first described in a story titled Reason in 1941 by Isaac Asimov, so I always have to give him credit.
How do they focus the microwave?
They don't. Believe it or not, you want them not to be focused. You want them all to come down flat. It's kind of weird. You just asked a really complicated question, but there's different zones from antennas, Fresnel zone, Fraunhofer, and what you want is, remember that equation that I showed you where as you get antennas further apart, that they have loss? These are set up so that as the distance goes back and forth within reason, the power exchange is the same. Yeah, I know. It's a difficult.
Can you use laser? I mean, can you send microwaves through laser?
The thing is, if you use lasers, you'll get blocked. First of all, if you have a thunderstorm, you'll block all the power coming down. If you use microwaves, they'll go right through it. So the idea is 24 hours a day, you get power. So yeah?
Sorry, is this like essentially like a lens, so that the microwaves are, I mean,
You don't want to lens it. That's the, yeah.
I don't mean like a lens, but, like when light goes through glass, it doesn't go through in a straight line, it's everywhere, and then it comes out the other, I mean, when you use microwave technology, does it mean that if there are clouds here and there and there, and not clouds here and there, it'll get through just as well as?
Mostly, at the frequencies they're choosing. They're trying to choose them, so they do. That they're choosing ones that this mostly is the case. You can, yeah, you can. Vertus Solis, you can go look it up and they'll give you the pitch. But this is, I like this because it's one of the more complex things I've done. There's the microstrip antenna, and this is just, there's metal on the back side here. There's a microstrip antenna. This is just a network that matches the antenna and keeps the electromagnetic wave inside of the printed circuit board. This is, these little things you can't see very well are harmonic filters, and those are to make the DC work better. And then there's a diode there that converts the DC, or the microwave to DC, and then you take the DC out there. And yes, it worked. So, yeah, the LEDs lit up.
Well, what kind of power are you talking about through something like that?
A lot.
Classified?
I don't remember right off, but enough you should think about it. You can talk to the guys. I don't remember exactly, but yeah, there's quite a bit of power coming down. Yeah, I'm consulting. I built this. This is what I built for them. Okay. And they did a big trial where they took a bunch of antennas I designed, huge arrays, and they put a bunch of these and they lit up a whole bunch of lights, and it was cool. And now they're trying to find more money, which I hope they do. So this is the only thing I've done, and I hope this doesn't get, this is the part I was afraid people would be concerned about, so have patience. Here's your little microstrip antenna in the middle here. And you can actually end up trapping waves. When the waves, you want them to come radiating off, but they can get trapped along the surface there because there's a dielectric, a plastic. Remember I told you how they'll bounce just like in the swimming pool? Well, if you take a look, there's a metal ground plane. You can take that out, and if you just have a dielectric in there, it's like it bounces back and forth and they get trapped here. This is known. It's been known. People have talked about it for years and years and years. So you remember this looks a lot like the waves coming off the dipole. If you remember the shape of those? Yeah. So it's very similar being driven. And this is the only thing I've ever done that's actually, I did some math. Scary? It's all algebra. It's scarier than it looks scarier than it is. So what happened is all the previous theories stated that the larger the distance, that metal ground plane, remember you asked, you know, what's the deal with the distance? Well, that affects how much power, if you put, you know, a watt in, if it's too thin, you'll lose half of it. So you need to thicken it up. But people noticed that, previous theory, all these great big long papers with lots of mathematics, and it said that as you increase the distance from the metal ground plane, these surface waves got bigger. So you make it thicker, and a lot of your power ends up getting shoved off into these surface waves and bounce around, and terrible things happen. I believed this. I 100% believed this. I had a company come to me and say, hey, you're one of the, at the time I was the only guy, I didn't realize this, that used a model to show that the previous theory's results. So I attempted to use what's known as full wave software. This is this new modern software that will solve Maxwell's equations and does it perfect and stuff. And I had to think how to do this. And when I realized it, I used software and I discovered this is exactly wrong. It's exactly wrong. So here is, remember the microstrip antenna, so you got just a hunk of copper, You got a hunk of copper down here, that's all it is. And you connect it here, and there's plastic here. And when I did the original calculation, this is in my microstrip antenna book, right here is the loss in the plastic, and it goes from 12% down to 3%. The conductor losses, and that's just like in that big horn antenna, go from 8% down to 0.61%. The surface waves go from 2.34% loss in the surface waves to 10. So as you make it thicker, you're throwing away more power, is just going away and not going into your radiation. When I did the calculation using the method I came up with, these are actually closer than you think. This one's like 12, this is like close to 11. When you get down here, you got 3.47. So these follow. So the losses in the plastic follow. The conductor losses, here this is 0.61, this is 0.55. These are really close numbers. And then on the last one, mine starts out at 15% when it's thin and goes clear up down to 3%. So it's exactly opposite. I thought this was wrong for the longest time. And then I had 2 or 3 PhDs look at it and had another 2 or 3 more look at it, and they said, we don't see a damn thing wrong. So I have no idea. I came up with different types of waves this might actually be. But this is the one thing that I can say, well, I did something in my life, I guess. Yeah, sure.
They weren't measurements, they were calculations.
Well, that's what was funny, was when I went to send the paper in, I showed this, and by the way, I've never seen HFSS be wrong. I also checked this with other software. They all matched. They all matched using my method. And they said, hey, you don't have any measurements. And this was solved in the 80s, and we're sure those guys in the 80s were right anyway. And I said, those guys didn't have any calculations or any measurements, why are they right? Well, they were going to bounce my paper and not put it in, and the editor showed up and said, I think this is important enough, we better publish this. So yeah, it is all theoretical, but I can tell you, what I've done is really, what's that?
So now there's no corroboration?
Well, there's a fascinating silence about this since, let's see, 2021 I published this. I've had 6 papers cite it, but not say anything about it. I had one professor, when I first published this, I had one professor who does these large complex calculations email me, and he said, you got to show me where I'm wrong. It's like, no, that's not the way this works. And then I had another guy working on his PhD, and he said, well, you've given me a problem to work on. And I've heard nothing back from him, so maybe it's a pretty rough, I think it's a really, really, really tough problem. But the thing is the method that I used here is so basic, anybody can understand it. It uses what's known as Q.
Why can't you build things that measure it? Actually,
oh my, it's very difficult to do. It is, it's very difficult. I can measure it indirectly. I can't measure it directly. I can measure the power in, and I can do these out, but I can't do a complete antenna measurement to show this is all true. I can do indirect measurements that show that it's true. They didn't want to believe that either.
Does that show up as power loss?
Oh yeah, absolutely. No, this is exactly what happened. Yeah, it does. And mine's right.
So then it would be measurable. I don't understand why it wouldn't be measurable.
Because I have to measure the surface waves. They won't disbelieve, they'll say, oh, sure, power's going away. But what makes you think that has anything to do with this? So it's been interesting. For me, it's like someone else in this room that I know, I'll let the theoreticians work on this one. I basically showed this. So historically, antennas have also been some of the tallest structures on Earth. The TV antenna outside of Fargo, North Dakota, KVLY, was once the tallest structure on the entire Earth. In fact, it was for a long time. You can look it up on Wikipedia, kind of interesting. And there it is. And there is the mast. And there's the Shanghai Tower, and then there's the biggest buildings on Earth. But for the longest time, antenna structures were the biggest, for just something to tell you. Antennas can also go Hollywood. If you ever get a chance, you might see the dish. It's a fictionalized account of a dish antenna in Australia that was used to receive signals from Apollo 11 and send them to us so that we could watch them run around on the moon. It's a little more, it's less, the reality is a little less dramatic than the movie, but it's actually a comedy, fun, it's actually a fun watch. So there you are, and you'll experience where the focus of the narrative is the importance of a dish antenna.
Randy,
Yes.
all the way in the back here.
Yes, Paul.
You know, I wanted to ask, because I think that every time I'm driving through the Midwest, you know, Iowa,
Sure.
Kansas, Oklahoma, we see all the huge antennas.
Oh, yeah.
And I always thought it was kind of trying to work on the curvature of the Earth to go as far as possible. Is that true, given your example of whatever it was, in Minnesota's?
Yes.
Trying to get distance?
They're trying to get distance.
Power or both?
They're trying to get distance. They're trying to get distance is what they're mostly going for. And feed. The other thing you have to keep in mind is that it really depends on the frequency, because that ionosphere only works at lower frequency that it bounces off. At UHF, at higher frequencies, it just goes through. So Marconi would have lost money, died, and no one would know who he was if he'd have tried doing it at 10 gigahertz or something.
Sorry, back
Sure.
to something you said some time ago. So you're saying that antenna transfers are actually, you get better results than optical cables now?
I didn't say optical. I said coax, any metal. Optics work pretty good, but they only work for a few kilometers. They have amplifiers on them to keep moving them.
And that's what,
And that's. But there's so much bandwidth in them. You can sense so much junk in them that it's really worth the effort. Okay, and here, I'm sure you're all happy. This is the final thing, is that you can't not just electromagnetic waves exist in this world, but gravitational waves. We actually saw those. And back in, I forget when it was here, but I think I decided I'd just read this, but the possibility of using gravitational waves to communicate the same way we do with electromagnetic waves was discussed in 1991 by John Krauss, who invented the helix antenna, the corner reflector antenna. Yeah, he's a big shot. He worked on what was called the satellite project in the 50s. And he said the difficulty of communicating by gravitational waves appear to be essentially insurmountable. What you do is you'll take a rotating bar, will do gravitational waves. If you remember, what we have is a couple of black holes doing this. This is way smaller. And so if you took a 20-meter long, and he was doing this back in 1991 before anybody had measured a gravitational wave, and he said, take a 20-meter long, 500 megagram, it's 500 tons, 500 megagram rotating steel beam as an example, the maximum rate of rotation that you can get is about 270 RPM. Above this, it just flies apart. The metal can't even hold it. It says, it would take about 20 hours to spin this thing up. And it would take 100 kilowatt power input and take about 7.2 gigajoules to ramp it up. It also would take 20 hours to spin it down. So in other words, you're sending one bit every 40 hours. So you're sending a 1 and then not, and then 1 and then not. The device would transmit radiated power of the gravitational wave would only be 10 to the minus 27th watts, which would be 0.001 yoctowatts. They've added more metric prefixes, but I'll go with this. That's using the smallest prefix at the time. While not zero, it almost ought to be. The gravitational waves that we've received here, if I remember right, they're more like 10 to the minus 24th. And so, this is even way worse. The radiated gravitational waves from this thing as it's spinning would be about 9 hertz. So it's not far off of the Schumann resonances, actually. And detecting this tiny amount of power, Krauss said, essentially, he threw his hand up a little bit and said, well, if we had this magical device that would take in a solid state and measure gravitational waves directly, we might be able to detect them well. So there's a magic receiving antenna down here. I just like it because it's the way Krauss thought. He always thought weird stuff. And this is pretty weird stuff. So I think I've tortured you guys enough. Okay?
On the way here, I was listening to, and one of the NPRs, CPR probably, and they were talking about all the solar activity, this
Oh my, yeah.
aurora borealis,
Yeah.
and that is inducing like antennas everywhere because it's a lot of power, and it's exactly this oscillation that you're talking about, so that every piece of pipe turns into
Yes.
an antenna.
Everything's an antenna. Everything's an antenna. And yeah, no, it's exactly, that's exactly what's happening is when it comes down, there's large electric fields that are created on the sun. They hit these conductors and there's electrons that have nothing better to do than get shoved by these fields.
And things in microchips can get fried.
Oh, yeah, yeah, and the noise in them is really bad. So, yeah. Yes, Paul? Oh, sorry.
You know, Randy, thinking about, radars and these waves and how it works, how is that? Can you explain to a layperson? How do stealth airplanes work? How can you get it that it evades the bolts of the radar?
Well, it doesn't evade it. It does two different things.
Layman.
Yeah, I'm doing my best. What happens is, you remember things reflect. So the earliest, if you look at the original F-117 at Lockheed, you'll see that the shape of it reflects waves. What happens is it reflects them away from it. You have to have, remember, for every transmitting antenna, you need a receiving antenna. So if you send the wave out to hit something and it doesn't come back, then you're there. It's as if nothing's there. So the wave will go out and they go, well, we're not going to have it reflect back. We're going to reflect it up and down so that it doesn't hit it. The other thing they do is they put materials on them that if surface waves are captured, it attenuates them. So you can grab those surface waves and they can go around things, but you can make materials that it comes in and it's just like acoustic tile, only for electromagnetism, and it attenuates it down. So, but by reflecting them away and by attenuating those that get caught on the aircraft, you get rid of it. Yes, sir.
So, just being a layman also, can you remind, oh, hello.
Yes.
Boy, we're going to get
Good
official
technology.
here.
Wireless technology.
Look at that. What's the frequency of this thing?
About 39 megahertz probably. That I know.
So, can you remind me of the frequency range of microwaves?
I don't remember the exact where they go, but I've always considered microwaves anything above a gigahertz.
Okay.
And then they get up to the point where they get close to millimeters in size, and they call those millimeter waves. So that's, by the time you get to 50, 60 gigahertz, you're talking millimeter waves. So about 1 to 40 maybe gigahertz.
Okay, so basically the antennas in our cell phones are microwave antennas. Is that right?
Yeah, well, some of them are yes, they are microwave antennas by my definition. The Bluetooth, the antennas actually, they're lower. They're just below microwave. Because they're about, if I remember right, because I used to actually design these. This is embarrassing. I can't remember the numbers right off, but it's about, I think, 800 megahertz for one of the bands. And it's somewhere in the 800 megahertz range. So that's just below 1,000 megahertz, which would be a gigahertz. And so they're just below microwave. But they want that also because the lower frequencies go through walls. So because of the wavelengths, the bigger the wavelengths are, the less they care about this stuff. It's small. And what you had was I had one antenna engineer who called me from another large company and said, they're talking about doing 60 gigahertz for this 5G stuff, Randy. What do you think? And I said, I just hope there aren't any walls, But the thing that you have to remember is the reason a frequency gets used is often a political question, not a technical question. Right. And I went to a really neat IEEE conference about a thing called synthetic aperture radar. Maybe you've heard of that before. What happens is you take an antenna and you scan the ground, and you go back along the ground, and through a bunch of magic we won't talk about, you can actually produce images that are really like photographs. And they did, this one satellite company was there, and I was talking to them, they said, well, we used 400 megahertz. Stopped, and the other thing that happened is they did Burbank, and everything looked really great. I mean, Burbank looked like a big black and white picture, and then all of a sudden it just disappeared in certain places. And it turned out it was because of the angle of the buildings were reflecting in a stealthy-like manner, place where that you don't want it to go, and it disappeared. And I kept saying, why did you use 400 megahertz? Why wouldn't you use, I don't know, 5 gigahertz or something, so you can, don't have these problems. And the guy finally pulled me aside, and he was honest. He said, you can get spectrum at 400 megahertz. Nobody wants it. And the guys who put this together said, we want to use that. So keep in mind, lots of technical questions are not answered by technical solutions.
And also, you said everything's an antenna. So are like the heating elements in my electric oven an infrared antenna of sorts? And these light bulbs are visible light antennas of sorts?
Yes, in fact, we used to have the old long tubular fluorescent. Remember those? Remember I was talking about noise temperature of antennas? One of the ways those are measured was basically a fancy fluorescent tube throws off a huge spectrum of noise that looks like a certain temperature. And so you put your antenna in front of it, and actually a lot of times you use the sky, but that's another way you can do it, is you can use these fluorescent lights. And that's, yes, they emit lots, the fluorescent lights emit a lot of radiation, and that's one of the reasons they actually have coatings on them to keep the UV from coming out of them and hurting you. Okay. Yes?
You use a lot of this, like multi-gigahertz frequencies. What kind of speeds do transistors have now?
Oh my God.
How high do they go?
I'm going to guesstimate that they're probably somewhere in the 20, 30 gigahertz range. I'm kind of guessing.
What do you do if you need to go above that? How do you?
Well, what happens is there's this thing called circuit theory, okay? And circuit theory by electrical engineers is if it's really, really small compared to a wavelength, you can pretend that electromagnetism doesn't matter. You say, I've got a resistor, water goes through pipes, and we can do it really simple models and make it work. So we got resistors, and we just, like water and stuff. So what you do is if it gets to a high enough frequency, you start getting microwave type effects. So they keep shrinking it. Why do they shrink it? Have you ever asked yourself, why does it have to be smaller? Why not just, Well, they make it smaller because the faster that you transition a transistor, you end up creating an electromagnetic pulse. And it'll start bouncing around like a microwave inside of there. So you keep shrinking it until it's small enough that those effects disappear, until you get to this thing called quantum mechanics. And then you start having real problems. So yeah, they keep shrinking them so that they don't have to do all this fancy math stuff that I do. They would have to, and it would make it so much more complex. You would get reflections all over, when you're sending signals, there'd be reflections all over the place. And so they keep shrinking it so that these reflections don't happen. What are known as mismatches is what they're called. So it's, yeah, yes, sir.
I think his question, though, is, you're talking about these high frequencies, but the electronics, the transistors, don't work at such high frequencies, or did I misunderstand the question?
I don't know how fast a transistor can switch these days. I know what size they make the traces, so I'm inferring from the trace sizes how fast I don't know how fast modern transistors switch, is the answer to that. But it's slow enough that that you can use circuit theory and you don't have to use all this fancy microwave, bouncing around stuff.
Randy?
Yes.
I have another question.
Sure.
The first one was on stealth airplanes. The second one's military related also. Let me say I'm not in the military, okay? It's just two examples I thought of. I recently saw an article where the Ukrainians shot down a Russian airplane. I don't know, I think a 35 or whatever. And the Americans were just gleeful because the Ukrainians gave it to the Americans. And they said by having this, they could figure out the megahertz or the, how it's sending pulses. Couldn't someone like you tell that without physically seeing it? Do you see what I'm saying?
Well,
they have the broken airplane, and from that, they can deduce what it's transmitting at.
Yes, you can. That's the reason on the atomic bomb that they didn't show the length, because if you can get the antenna and you can look at it and you know what kind of an antenna it is, you can go, it's working at this frequency. So the minute you have it, it's not classified anymore because we have it. We can even take the antenna out and, we'd leave it in, but we can hook something up, measure it, and see where it works even at that point.
Exactly. I was curious because they say that they jam now the, what do they call those things? The drones.
Yes.
So have they gotten a drone to look at how big the antenna is? Or are they guessing?
They can.
Or they just throw out everything at them to try to disrupt them?
It really depends on the system. You may have heard of things called spread spectrum system, like the GPS system is that way. You take, and instead of saying, I'm going to work at this frequency and send a signal at this frequency, I'm going to spread it out over a ton of frequencies and make it really low level. And then you grab them, all those frequencies, and shove them back together, and you can see it. And so it's hard to jam that because you've got all these frequencies. But if it's a very simple one, and it's just using a single frequency, 2, 3, 4, you can set something up and jam them. But the really bad thing that's happening, in my view, right now, is GPS jamming. They're taking GPS frequencies, and they're just faking out aircraft and other things and saying, no, you're not on that side of the earth, you're over here, because our signal's much stronger. I in fact called it a long time ago, and no one believed it at the time. You may remember that the Iranians ended up with, I can't remember if it was our drone or somebody's drone. I'm about 100% sure they used a GPS spoofer. They just created a fake satellite on the ground, overwhelmed it, and said, nah, you're not, you're over, I don't know, pick a country that, the U.S. has landing in. And as it's landing, it lands in Iran. So,
yeah, that was famous. And I think they got an American drone, if I remember
yes,
correctly.
I think it was an American drone. But there's two things called ECM, which is electronic countermeasures. So you can try to jam things. And then there's ECCM, which is electronic countermeasures. So then you counter that to counter this to play with that. And there was actually in World War II, you can look it up, a thing called the Battle of the Beams that was pretty interesting. where jamming was involved in trying to deal with Allied planes and a number of other things.
Thank you very much. Thank you for keeping us on our toes.
Okay, I hope it was okay, guys.
Thank you very much, Randy.